Okay, so I am actually just the warm-up act for this panel. We have 3 panelists here, and we're going to talk about deep learning in computer vision. And so the idea is that we're going to have a little bit of a kind of a warm-up about our views and some of the recent research on the topic, and then hopefully we'll have time for some discussion. So I'm really just going to give you a little kind of a warm-up of my view of what is going on with deep learning and computer vision. So it used to be that data got no respect, right? So this is the famous story that if you want to publish a NIPS paper, first you need to come up with a beautiful, clever algorithm, hopefully a graphical model, lots of bubbles and arrows, and then like a week before the deadline, you say, okay, I need to find some features, and then the night before you say, oh, I need some data set to run it on, and then you submit and you get an oral and everything's great, right? Except, of course, if you wanted to start a company, and this is a quote from Amnon Shashua, the Mobileye person, he would say, no, you start with the data, and then you find some features that work, and then finally you do some kind of algorithm, or you try them all and you see which one works. Okay, and so there's this kind of dichotomy thing. Okay, and for me, just like Michal and Ira, actually, data was always very much important. And so this is you've seen some beautiful work from Michal and Ira already. Here is a little bit more kind of inspiration that really data can get you a really long way. So this is just a little silly project. You have an image, and then you didn't want this picture in the front. You get rid of it with Photoshop. Okay, great. But now you have a hole. How do you fill in the hole? Well, you download 2 million images from Flickr. You do nearest neighbors, and you get something like this, right? Or a second nearest neighbor, third nearest neighbor, and then it, maybe sometimes it doesn't work. Okay. But you don't like your view from the hill, you can switch to the hill, etc., etc. So why does it work? Well, it really works because of the data, right? So you take this image, and we started with like 20,000 images. This is 2007, so 20,000 was the biggest, big large image data set ever, right? We thought, wow, it should totally work. And these are the nearest neighbors, and they're not very near, okay? But then exactly the same code, exactly the same algorithm for 2 million images, started to work. So it's really, a lot of this is about the data. So the good news is really dumb algorithms plus lots of data gets you what is called this unreasonable effectiveness. Now, of course, there is bad news. And the bad news is that this requires really a huge amount of data. In the general case, if you're not content with some subset of the data like Flickr images, if you really want to model the entire visual work, you do require a huge amount of data because you're not really taking advantage of any compositionality. There's no disentangling of any of the sources, right? We're not doing anything as clever as Michal here with compositionality, right? This requires a huge amount of data. It's also computationally expensive. Runtime is order n. And of course, it's really hard to find out, what are the good distances? What is the distance? How do you measure what is the closest thing in data that you need to find? And computing distances is hard. It's easy in numbers. It's not that hard in strings. Even for pixel brightnesses, you can compute difference between pixel brightnesses. But what's the distance between those two things? Nobody knows, right? These two images, we feel like they should be close. But if you look at pixel to pixel, there's not a single pixel in common between those two things, right? And this is where semantics comes from. Because you say, well, if I tell you that both are called penguin, maybe that can kind of help you out. And this is where basically machine learning comes in. Is this kind of a little crutch that says, well, if I get you a little bit of labels, maybe you can do better, right? So you can think of machine learning, supervised machine learning, as this data association problem. You're associating your data X with some label Y, right? And so you give lots and lots of data, lots and lots of data, and then for a new image, it can spit you out, oh, it's a label, okay? And the black box here that is particularly useful now is the convolutional neural network. So why is that black box become so important? Well, one is that it's particularly good at eating up a lot of data. You really want it to have high capacity, and this black box has much higher capacity than many other parametric methods. So it's still not as good as non-parametric methods, but it's much faster than non-parametric methods. So it has a lot of capacity. But there is more to it, because if you think about kind of the old style object recognition, right? So what do we have? We had an image, and then we computed some low-level features, edges, textures, colors, and then from those we computed some mid-level features, segmentation, parts, etc., figure ground, and then from that you can try to figure out if it's a penguin, and you know, this could be learned. This classifier could be learned, but it didn't need to be a very complicated classifier, right? It basically some very simple linear thing was enough, because you were almost there. You already got almost to the place where you had the segmented, you have the segments, you had the color, everything was already almost there, right? But of course, getting all of these to these boxes was very hard. How do you know what's the right mid-level representation? What's the right low-level representation? And so in fact, and you know, in the early 2000s, people started to say, well, maybe we can learn low-level representations too. Maybe we can learn good edge detection. Maybe we can learn good texture representation, learn good color representation, etc. So the learning started to creep into the low-level things, but then you have to somehow label what is it that you want, and that was hard too. And in a way, if you think about the neural network, it's basically just all of these things combined, right? So it's basically says, I'm going to come up with some sort of low-level representations, which will then feed to a mid-level representation, which will then feed to whatever you actually, the label that you want. And every step of the way, it's very simple. Every step of the way, it's not a big thing. It's like a linear classifier, basically, right? But altogether, and kind of the nice thing is that you don't need to actually, you cannot say, okay, this is edges, this is texture, this is color, right? That those labels are gone, but maybe that's okay, because maybe you didn't really care about the intermediate representations themselves that much. At least sometimes you don't care. Maybe really all you wanted to do is this task, and at least the promise of deep networks is that it will figure out the right representation for you, okay? And so in a way you can think of a neural network, these three boxes that I talked about, it's kind of all in here. There is the algorithm, there is the features. The features are basically part of that network. It computes its own features and then uses those features, right? It's kind of like a snake eating its own tail, right? And the data is also in there, because even though each one of the classifiers is kind of silly and simple, there is so many of them, and they have so many weights, that in the end you end up with millions of parameters. So you actually can capture a lot of data. Okay, and so that's why you have this, very cool results on something like ImageNet. I'm sure everybody have seen this. Image captioning. You can see these amazing things like a group of people posing for a picture on a ski lift. It's like, wow, this is crazy. How, right? This is insanely good, right? So, is computer vision done? Well, hold on, not quite so fast. There are some challenges, right? One of the challenges is the visual world has long tails, right? So what does that mean? It means that there are generic things, the things that happen all the time, and then there are kind of specific things that they're more, they're things that happen very, very rarely, and they're all different individual ones, right? And in a normal distribution, this is where your mass is, and this tail kind of vanishes very fast. Well, the problem is that for visual world, that tail is long. Okay, so that means that the unfamiliar is actually common. The tail maybe is as heavy as the body of the dinosaur here. Okay, and so this means that if you're trying to label everything in the world, you'll have a lot of things that happen very, very rarely. And that will be very difficult for you to find good enough, enough data for all of these little things that are in that long tail, right? And this problem is particularly exacerbated by the problem that when we train this, we train on some data sets, and the data sets have their own particular biases. For example, here is an image, and you run a image caption on it. I just did, and it says a car parked on the side of the road. Magical, right? But then if you search for car on Google image search, which is where all of those data sets come from, yeah, basically they all look like they're parked on the side of the road. So every single image here, you could fit that caption to it, and it would look okay, right? And if you try it on some real-world scenarios, which you would actually run into, in an actual real driving scenario, it might not work. Okay, so maybe you might not run into this that often, but sometimes you will, and it still thinks it's car parked on the side of the road. Turns out, guess what? This is also car. There's a car. There's a road. Maybe it's parked. Challenge number 2. The classifiers are easily fooled. So this is a famous example of you take an image and then you add a little bit of noise. It's a special kind of noise. It's kind of a noise that pushes it to look more like an ostrich to the network. For you, it's exactly the same, right? But for the network, it basically totally looks like an ostrich. And so here is a whole bunch of images and their labels are underneath that you fool the network. Not too surprising, but something to keep in mind that this is, it's a classifier, right? So it's not guaranteed to behave, to do anything reasonable off the natural image manifold. Probably my favorite example of this is this work from Leon Gattis, who did all of the style transfer stuff. So he took an image and then he basically used the kind of a texture synthesis to just perturb the image to make random permutations of the image, basically treat it as texture and then make different instances of this texture, and then run it through ImageNet classifier. And what you can see is basically the classifier was just as happy to label these as whatever Collie or whatever the right answer is as this. So basically it suggests that when we're talking about object detection or object classification, it's really texture classification. We're really at this point still kind of in the texture regime. I mean, it's kind of impressive that it works as well as it does, but I think we have to be aware of this. Another example. Challenge number 3, labels are expensive, right? So all of these labels, where do we get them? Those people clicking on Penguin that Fei paid, I think 2 of her startups from 2 universities were spent on people labeling the ImageNet data set, right? This is very expensive, so you can't really go to really huge amounts of data. So going back to those long tails, the long tails become more and more expensive, okay? Challenge number 4, there are more things in our visual world than there are words to describe them. So here's an example. In the visual world, we have Pittsburgh and we have Paris. Somehow in English, they all happen to be called the same thing. They're called a city. But if you look at them visually, there is nothing in common, right? You can say, well, they all have buildings. But look, the buildings are very different. You say, well, but the buildings have windows. But the windows look very different. Everything to the very end, it's really, the visual world is much broader. So you can't really have a one-to-one correspondence. So if you're labeling visual things with words, you're going to lose a lot of information. Okay, so the words, I call them the visual, kind of the language bottleneck. It throws a lot of the beautiful visual content. So one argument that a bunch of people have been talking about, and this is hopefully leading into what Rob is going to talk about, is this supervision, especially supervision by semantics like words, may not be the right thing because of all of this issues that we talked about, right? Because if you think about it, step back and say, why do we have vision? Why we humans have vision, right? Well, Aristotle and David Marr had this answer, to see what's where by looking. It's a beautiful answer, but it's a little bit, how should I say, short-sighted, right? Because why really do we have vision? We didn't have to look, right? Well, if you go deeper and deeper down the rabbit hole, in the end, there is a Darwin and Dawkins explanation, right? We have vision to make babies who have babies who make babies, right? That's the loss function of evolution. So this is what, in the end, that's why we have it. So that's maybe a little bit too far. Can we get somewhere between those two? So I would argue, and I think that Rob might actually agree with me, is that predicting the world or predicting how the world is going to affect me is probably the most important thing for the visual system. That might be why the visual system evolved. It's not to see what's there at this moment, but to figure out what is going to happen, what is there, what is building a model of the world and then seeing when the model is right or not, right? And so the cool thing is that if you make a prediction about the world, you just have to wait a little bit to get your training data, because the world is going to tell you if you were right or not pretty soon, right? And so this idea of some people call it self-supervision, basically having the world, having the data itself, supervising yourself, is I think very powerful. And so you can think of it as using, instead of words, using labels that come from the data itself as very, very exciting. And hopefully we'll see some of this. And I'm going to talk about this when I give my other talk 2 days from now. But just to convince you that humans are really, really good at this prediction task, there is a beautiful video of young Rob. So it's very blurry, right? But we can all predict. We can really kind of hallucinate what Rob is doing. It's very low resolution, but Rob is working on the computer. He's listening to music, right? Young Rob at MIT, back in the old days, no worries at all, right? So we are really good at basically hallucinating, what's actually happening here. In fact, we are a bit too good, because this is really what's happening. This is Rob talking on his shoe. And then he is going to put on his Coke cans. And then he is going to use the mouse here, the stapler, and check out the printer, and actually the monitor. Yeah, this is how. So this is a beautiful seg to introduce our next speaker, Rob Fergus, who is a very serious researcher. My usual introduction of Rob is that you can never outrun or outdrink Rob Fergus, so don't even try. Why don't you set up? But more seriously, Rob Fergus has been one of the most influential researchers bringing computer vision into the deep learning era. He basically took it upon himself to say, okay, Jan LeCun, I'm going to figure out what you are talking about, and I'm going to really understand it, and I'm going to explain it to the vision people, because you're not explaining it right. And everything I learned about deep networks was really from Rob, because he really explained it in a way that was made sense, and he was the one who did this beautiful visualizations, because I always wanted to see what's happening inside, and Jan didn't care. But Rob made this beautiful paper that actually showed you what is happening inside, and Rob continues to do some really fantastic fundamental work in this area. And so, I guess the latest stuff. Give him the mic. Huh? Give him the mic. Oh, Mike. Sorry.
Alyosha is obviously a tough act to follow.
No.
What I'm about to say will be a lot less dramatic. So I'll try to. All right. Okay, so all right. So as Alyosha was motivating, we want to sort of think about how we can learn without this burden of sort of having to have manually provided labels everywhere. And I'm going to sort of make an argument, which is perhaps not exactly the one that sort of vision people use, but I think it's nevertheless a compelling one about why we should really be thinking about trying to predict what's going on in the world. And I think this is actually a very important sort of topic for vision people going forward, and it's very much an unsolved problem. But I'm going to be talking about in the context, as you'll see, of a very simple world, not trying to do it in the context of general video or anything like that at the moment. Okay, so just to be clear, what we're talking about with this predictive learning problem. So you're going to be given a video, and you'll get to see some section of the video up to, say, the current time. And then the idea is you've got to try and predict what's going to happen next, and so on. So you're going to build a model which will take this history, come up with some prediction for the next frame. And of course, the beauty is that if you just wait a bit, you'll actually see what actually happened, and then that difference is going to give you some kind of error signal that you can use for updating your predictive model. And the hope is, of course, that if you can come with a really good model of how the world will be in the future, then somehow you must be sort of understanding the world itself, right? You must be understanding the sort of the objects, what they're doing, their actions, and so on and so forth. And the beauty is, of course, that there's no explicit labels you need here, right? You just have to sort of have your algorithm sit on the couch, just watch TV, and there's essentially effectively unlimited amounts of data that you can get for this kind of thing. So the model has to essentially internalize just how the world works. And one of the big challenges, as I'll talk about in just a moment, is really that the world is unpredictable, and therefore the models we've got to use, I think, to be able to do this effectively, will have to take into account this kind of uncertainty. Okay, so now I just want to, so now, if you look at a lot of the current papers that are being published at the moment, people are thinking about these sort of unsupervised learning approaches as ways to kind of get a good feature representation without using ImageNet. Okay, so the idea is, if you do this, maybe the features inside your predictive model will be good, will be sort of, there'll be high-level information there that you could easily train, a good object recognition model, say, off very few examples, right? You wouldn't need those millions of images from ImageNet. And I think that's, certainly an interesting thing to think about, but I think there is actually a much deeper motivation as to why you want to do this predictive modeling. Okay, so I'm just going to spend just a minute or two just giving that motivation. Okay, so I think what I want to think about for just a second here is how you would actually build an intelligent agent. Okay, and Alyosha just touched on this just at the end. In fact, Jitendra also was sort of alluding to this in his talk too. So the idea is you have the world, you have an agent, a robot or something like that, and it's going to perceive its environment, so it's going to get images or some video stream, and it's going to be taking actions to move around in the world, to pick things up and so on. And it has to sort of pick the right actions that will maximize some kind of objective function, find more food, or sort of increase your happiness and so on. And so the question is, of course, how does the agent decide what are the good actions to take? So if you sort of zoom in inside the agent, this is a slide from Jan, who I'm borrowing here. What you see is that the agent, if you think about it, really has to have a model of what's going on in the world. It has to have this world simulator, which is effectively this sort of predictive model of what will happen if the agent's standing in a certain position. He has to think, well, if I push this chair with my arm, will it touch the other chair, and so on. So there's essentially this idea that you have to have inside your agent a predictive model of the world, which will let you essentially say, well, if I take a certain action, what will happen? And then you have some essentially internal model of a critic, which will say effectively, how will this affect my overall objective functions? You have to have some models to decide, whether that's a good action or not. And if you have this kind of setup, then effectively you can kind of unroll this over time, like so. So you can sort of take hypothetical actions, and then conditioned on those, you'll know what the world state will be, and then you can sort of keep going forward like this. And this lets you effectively plan, so you can without taking any motions in the actual world, you're able to sit and sort of try out different possibilities and just try and find a sequence of actions that you think might be good in terms of your overall objective function. Okay, but to do this, the hard part is really this box here, right? This predictive model of I'm in a current state. If I take this action to say walk one step forward, what will be my future state? But of course, you don't want to actually take the action. You want to just sort of hallucinate it in your head. Okay, so this is just to make the point that this is a sort of a concept which has really been around for quite a while. There's a lot of people, philosophers, psychologists, and reinforcement learning people who've proposed this kind of general sort of way of thinking about things. And so I guess what I'm going to talk about just for a few moments is some work I did earlier this year with some folks at Facebook, which was to take a very, very simple world. It's just the world of sort of toy blocks, and trying to sort of basically predict what will happen, given, say, just in this case, not even a video sequence, just a single frame. So you're given a single frame, and we want to try and build a model that will predict. We're actually going to try and do two things. One, to say, will the tower of blocks fall over? So is this a stable configuration or not? And then the second thing is, which is a little bit harder, which is to sort of predict where the blocks will be, 1 to 4 seconds in the future. Okay, and we're not going to. I'll come back to this point in a moment. We're not going to directly work in pixels. We're going to just work in sort of, some sort of segmentation masks for each of the different blocks. Okay, and this is, in some sense, what we're trying to do here is build a very simple forward model, right? We're trying to, predict the outcome, into the future. Okay, and so to do this effectively, the model has to sort of implicitly capture what's, both sort of the mechanics of how the world works. And admittedly, it's a very restricted world, but it's one that we can easily sort of play around with. And so, so as we'll see, essentially we're going to generate a lot of synthetic data for training, and then we're also going to collect some real sequences, because you can obviously make little toy wooden blocks, and we're going to see how the models do in those two settings. Okay, so so the data. So what we did was we actually got sort of one of those video game engines, something called Unreal. So this is something is an open source game engine, and we sort of hooked it up to Torch, which is on the deep learning frameworks. And actually, if you want to, you can actually download this kind of plugin basically for Unreal. So this lets us programmatically kind of control the camera position and the block configurations and so on. And so we can generate a lot of videos here of these towers of blocks falling over. And of course, because it's the graphics engine, we can get ground truth as well. So we know exactly the positions of the blocks at time points in the future. And we, of course, you want some variability here because we want to be able to sort of the models to generalize different viewpoints and to backgrounds and so on, so we can sort of vary those in the game engine too. Okay, and then we also have a mix here of sort of stable and unstable configurations. So this is the data we're going to train the models on. We also, we'll use a held out subset for testing, and then we also had some real data. So these are some blocks that I made and spray painted different colors, and then we, just recorded some sequences of these things sort of falling over. And some of them were also stable as well. All right, so we're just going to use this as a kind of test data to see, if our predictive model does generalize to, sort of to real data, not just to the synthetic stuff. Now, the model we're going to use, you might guess, we're going to basically try a deep net for this problem. So there's a bunch of different ways of. In a second, I'll just say, mention some other sort of philosophies you could use for solving it. So the basic idea is you're going to take a single frame as input. We're going to take a sort of a ResNet trunk. So typically this will be a pre-trained on ImageNet. I'll show a few experiments where we actually didn't pre-train it. And then we're going to basically stick a sort of head on the top of the model. So we're going to throw away the sort of classifier that we would use for ImageNet and plunk on alternate architecture. And that's going to have two different heads to it. So the first head is really going to be just a simple sort of scalar output, giving a sort of probability as to whether it thinks the thing will fall or not. And then there's also going to be a head here, which is essentially a convolutional pathway, which will try and predict these label masks for each of the blocks. Okay, so we have in each pixel, you're actually going to have a discrete set of possibilities. Is it background, the green block, the yellow block, or the blue block? And so we have this sort of simple per pixel cross entropy loss, and we'll have a separate sort of branch for each time step into the future. Okay, so we've got three different heads here. Okay, and just some important points to note here. So we're not trying to sort of predict in the space of pixels, right? We're not trying to directly predict, the sort of texture, of the scene and things like that. It's actually much easier to predict these sort of things. We just have to worry about the sort of colored blobs, basically. And because we have this kind of discrete output, then it turns out it's much easier for the models to sort of work. And this raises the general question of, what space should you be doing this predictive modeling in, right? Should you be trying to predict pixels to pixels, or maybe should you be trying to do it in some sort of higher level space? The second point to make, this is completely bottom up. We're going to sort of brute force this whole thing with just tons of data. There's a whole, other folks out there like Josh Tenenbaum and people like this who are thinking about, these much more elaborate sort of top-down models where you actually have some giant graphical model that's basically a graphics rendering engine that would sort of try and do the same task in a very different way. And then the other point, I guess, to say is because we're doing it completely bottom up, there's we're not explicitly giving any information about Newtonian physics here, Newtonian mechanics here at all. It's essentially just being sort of has to be internalized just through tons of examples. Okay, so we did train this thing on several hundred, a couple 100,000 examples, which is doesn't seem that part of it doesn't seem at all realistic in some sense, right? That's an awful lot of examples, perhaps many more than a human infant would perhaps have available to it. Okay, so yep, sure, yep, sure. Okay. Well, No, there isn't. So training time, of course, yes. If it doesn't fall, then the blocks will just stay still. If it, but there's nothing actually explicitly forcing it to do the same thing. Yeah.
So you didn't really try to understand the sim itself, like you didn't try to understand the materials. Or
No. Well, okay. So I mean, these are the density of the blocks and thus the mass of the blocks is actually identical. So I'll give you some introspection in a moment as to what it's actually doing when it solves this task.
your model and your real images is the same material.
No, that's true. So it's not. So that's possibly one of the reasons why it doesn't generalize quite as well as you might hope to the real things. Yeah. So there's a sort of interesting point there. Yeah.
What about recurrent network to predict the next?
Yeah, that's right. I guess in this we could have done that something up there for sort of for over time. I think we just we're only doing 3 time steps. We just thought it'd be simple enough just to operate from to not bother with any recurrence or anything.
Giving a probability distribution over each cell being.
That's right. So exactly. So each pixel is going to have a probability that sums to 1 over being background, green block, blue block, yellow block. Okay. So just to show some results here. So these are different. This is accuracy on the simple full not full task, and this is on the synthetic test set in blue, and then the real images in red. So this is some simple baseline. So this is a sort of nearest neighbor baseline on ImageNet features. This is if you just take ImageNet features and stick a very simple classifier on, you can see it sort of doesn't do awfully well. If you take train GoogleNet from scratch on this data, so you just have random weights initially, it does actually do pretty well, which is interesting. The filters look like complete garbage. So it's very unclear it generalized to any other task except predicting full not full, but it does actually do it pretty well. It's interesting, but you do see that the performance on real data is actually not very good. This is if you take, sorry, let me just rephrase. This is if you just train on the full not full task, okay? All these architectures. And then if you bring in the joint problem of trying to predict the label mask and full not full, then you do get some slight gain, okay? And so the performance on real data is clearly a big gap here, but it's worth noticing actually the real data is genuinely harder. So when you take humans, on the real data, humans also do pretty poorly, in fact a lot worse than they do on the synthetic data. And it turns out that the model is actually a little bit worse than humans on real data, which is never seen in training, of course. But on the synthetic data, it does actually do a fair bit better. I mean, obviously, it's got the advantage that it was trained on several 100,000, whereas humans, were only given a relatively small subset to sort of train on, just to get their eye in before they were asked to evaluate a small set. Okay, so and it's worth also noticing actually that the full probabilities actually between the network and humans were actually quite highly correlated. So there were examples which the humans found confusing, and so did the network, and things like that.
Human errors for even real programs.
Uh-huh.
Error is which way? 0 to 1, 1 to 0? Or
this is accuracy. So you want to be higher? Sorry, I missed how much I understood the question.
The full prediction means.
Oh, I see. Yes. Sorry. This is So if it predicted, it's 1 if it correctly predicted whether it would fall or not. So it's if it stayed put, then the model should be predicting 0.
My question is, that when you say error,
Yeah.
accuracy,
Yeah.
do you distinguish? I am interested in knowing.
Oh, I see.
whether
Yes.
error
I
is
understand.
false
Sorry,
or
I got it.
not
Okay.
false.
So yeah, I think. Okay, if I recall, for the synthetic data which it was trained on, then the errors were fairly equal between, the false negative and the false positive case. So they were balanced. In this one, I think when you try to transfer it to the real data, the model was consistently pessimistic, and it overestimated the probability of falling consistently. So that the two wasn't balanced anymore.
I guess a human will probably have quite a bias to one direction.
Yeah, that was it. We tried in the training data so we had to give humans some training examples here just to get their eye in. So in that we did mix it 50-50. So they the hope would be that they wouldn't have some crazy bias towards it always consistently falling.
Yeah, test data.
Right.
I'm interested in the real,
Uh-huh.
not that.
Oh,
That's a test correct data, right?
Yeah,
You
right,
have
right.
a 50% of fall or not fall.
That's
The
right.
real one.
That's right.
My question is, when you say human data error,
Yeah.
is it fall made to not fall or
Yeah,
not fall to fall?
Yeah, I don't have the numbers here.
I
I'm trying.
think that might be
um,
interesting data to see.
Yeah, I have to confess I don't know the numbers off the top of my head. Yeah. I mean, just off the top of my head, I think they were reasonably equal, but it wasn't some crazy skew particularly. Okay, so one thing you can look at here is just to try and understand what the model's doing. So what we tried was taking the original image. This is, a test example. You would just take a sort of diffuse gray blob, and you're going to sort of put this down at a certain location in the image, and you're going to see how it affects its probability of predicting whether it's going to fall or not. Okay, and so in other words, if you put it on sort of the critical interface, where you're trying to make the judgment call about how far is the block over the blue block over the center of mass relative to the green one. If you block this part here, then unsurprisingly, you can see in this the sort of brightness of the red tells you how much the probability will change. So you can see this gives you a way to sort of, it's like a sensitivity map, in other words, as to what the network's looking at. In other words, the network doesn't really care about what's going on down here. It's really looking at this sort of region up here in the image. And similarly, down here, you can see it's looking at this sort of the stuff at these bottom two blocks and so on. So it's sort of kind of doing the right thing. Now, the other thing we did, of course, was to predict the label masks. So this is the ground truth. These are the sort of predictions from the model. So you can see it's actually doing something reasonable. It seems to understand roughly where the blocks will fall. You can see for these more complicated scenarios, it still does an okay job. It gets a bit unconfident as to where things are going. And I think this touches onto a sort of fundamental problem. Let me just show you. Hold on. So it does sort of generalize to the real blocks. Not quite as well in terms of predicting what's going on. So it's never seen these, of course, during training. So this is just purely checking the generalization. Now, one important point I just want to mention is, so let's just look at this example here. Will the green block fall? So the yellow one for sure is going to tumble. But you think, well, maybe the green one could still stay put afterwards. So and if you look at what the model predicts, so the model isn't sure. So it puts some of its mass sort of saying, the block might stay upright, and but it probably, the rest of it seems to go down onto the ground. And what it comes down to is, oftentimes you just can't be sure what's going to happen in the future. And so what we're doing here, of course, is forcing the model to make a sort of specific prediction, which isn't really appropriate. And what you really want to do is to capture this sort of distribution of possibilities. So what you really like is some sort of model that you can sample from, and then some samples, of course, would have the block sitting up there, and the other samples would have the block on the ground. And there is recently now techniques that let you do this kind of thing. So this is this whole idea of generative adversarial networks, which I'm hoping someone will explain at some point during the course of the school. So Alyosha, Alyosha's going to do it. Okay, wonderful. So at a very high level, what this does effectively is to capture a distribution of possible outcomes, not just a single possible thing. So just to show you an example here. So this is one scene. This is the target. After a few seconds, this is what the FizzNet would produce, and these are samples from this model. So you can see it's sort of sampling possible outcomes, and you can see that sometimes it thinks the tower will stay upright. Other times it's going to putting the blocks on the ground and stuff like that. And it's sort of, it's still kind of noisy, but it's an attempt to sort of overcome this issue of a kind of inherent uncertainty in what's going to happen in the future. And so I think what you're seeing is, like, for these predictive models, people are now very much looking at these kinds of techniques to try and handle this. So instead of just having some sort of mean squared error or some sort of per pixel objective function like we had earlier, you want to have this alternate mechanism that lets you really essentially generate a distribution over possible outcomes and use that instead. So just to wrap up, I think these predictive models are really a sort of key part of solving AI, right? I mean, they're useful for sort of perhaps doing away with ImageNet for training our visual representations. That's true, but I think this building good predictive models is sort of something we can't really avoid. And I think the deep nets do have some promise as a predictive model, but you've got to handle this uncertainty problem. And so there's recent work, so from Jan and some of his students have applied these generative adversarial nets on video. So this is what you're seeing is a little video sequence, and when the border's red, that's when it's generated. Okay, so the fact you see it looks sort of coherent into the future tells you something about the fact that the model is able to sort of come up with some reasonable predictions. And if you just use mean squared error on the between the predictive frame and the true frame, you get all kinds of blurry mess. And the fact that things are sort of still fairly sharp when you try to in your predicted frames is the fact that you're using this generative adversarial network loss function. And the other point to make is if you really have a real agent, like a robot running around, obviously here we're just sort of sitting on the couch just watching videos, but if you have a robot running around, which can you know the action that it takes when it moves its arm and so on, and then you can use that as an implicit label, right? That's a sort of free label that you can use. And there's this really nice paper that Jitendra mentioned very briefly, but I think it's a super nice idea, that has a predictive model in it that predicts the next frame, but it uses the sort of known action that between frame xt and xt plus 1 as a sort of implicit, as a sort of free label that constrains the whole sort of learning machinery. And so this is actually a very nice paper which was appeared on arXiv recently. So there we go. Okay, that's my little sort of position.
Just in time slide compiling.
Sorry, you need the mic.
Okay, and so basically what I'm going to talk about is like also what Alyosha already mentioned is what the thing which is becoming more and more important in this deep learning era is the training data and then the network structure. So I'll not discuss the network structure because I think today it's kind of still not really clear what are the good structures. So that's, I think, something open. But for the training data, I kind of have some ideas. So basically, supervised, we've seen yesterday, all these companies, they have like, it's not working. They have all these labelers who label data in India. So they have, like, I don't know what they said yesterday, 2,000 people just annotating the videos and the car scenes. So basically all the companies have that nowadays. And you could say, actually, are we done? We just build up the companies. They all sit there and label day and day. And so actually, so I think it's interesting that this labeling takes...
It's also a good idea because you have all these people out of work who used to be drivers. So now they can be labeling. It's good from a social standpoint.
Okay, it's good from a social standpoint, but maybe it's more interesting to drive than to label. But that's another question anyway. So basically, so why do I not believe that's the end of the story? Because okay, fine. I mean, Yara is saying the opposite. We'll put everybody back to work now. But basically, we cannot. We don't know also what everybody wants to label. It's very many things actually very difficult, intrinsically difficult to label. So one example is optical flow. So even if you have 100,000 people labeling, you cannot label optical flow. So the second example, which I'll show, is for 3D human pose. So again, labeling 3D human pose, maybe it's possible with a good interface, but again, it's very difficult to do it manually and to be sure that it's correct. So there are examples where this doesn't work, and then the third example is maybe the granularity. In many cases, you don't know what the granularity of annotation you want, and then going back and forth all the time is tedious. Okay, and so basically, I thought actually Alyosha or they were talking about weekly self-supervised and unsupervised, so there weren't anyway. So basically, there's a line of work which does things unsupervisedly. So for example, from videos, you hope to discover the features, and that's things which start to work, but they're not yet there. And the two things which I think are promising, at least in the short term, is weekly supervised learning, and then another thing which I mentioned before is training with synthetic data. I'll show two examples for each of those. Okay, so basically semantic segmentation. So again, basically you probably don't want to sit there day and day and label all the pixels. And so two ideas here. The first one is actually to integrate motion as a supervision signal. So if you want to learn labels from weekly supervised data, so for example here you would have the label car for this video. And what you want to do is you want to learn the car semantic segmentation from these videos. And so what you actually have some weakly supervised or unsupervised motion segmentation, which segments the object in motion and background, not always perfectly, but you can use this as an input signal jointly with a CNN architecture, which predict over time the segmentation based on motion and the segmentation based on segmentic segmentation. Then you train this network end to end, and you can actually see that from this data can very well learn the motion, the segmentic segmentation. And if you look at the results, so here this would be the just unsupervised labeling, and then here this would be the label prediction. So you can really, just by taking these very weakly supervised videos, you can really learn what the semantics labels for the object categories are. This gives you one idea, and here just an example to compare. This would be comparison to fully supervised semantic segmentation. Here it's EM-adapt, one of the state-of-the-art approaches for weakly supervised semantic segmentation, and here our approach, and you can actually see that it learns the object boundaries better.
Can you repeat again how you do your weakly supervised? Sorry.
So it takes as input the motion segmentation jointly with the label. So it has like one branch which does the label prediction and one branch which has the motion segmentation, and then on the fly it updates both of them. And then the second, so basically then the second question is, can we improve motion segmentation? And so here we actually looked at using synthetic motion segmentation data. So there's this flying things data set from Thomas Brock's, where you have many different objects flying in some unrealistic environment. And so what you have is then you have some optical flow plus the object segmentation. And then the idea is actually, can we train object segmentation, just like plain foreground-background segmentation, based on this very weak labels, and then in the long term we could just inject this learned motion segmentation in our previous approach. And so the network we use here is a U network, so we downsample and upsample. Again, it's similar semantic segmentation, but here what we learn is we learn for a neighborhood, is there an object moving or is the object not moving, right? So basically it kind of seems strange if you come from the geometric viewpoint, but it makes totally sense when you just look at different illusions at the neighborhood, and you see if there's some changes, characteristics changes in the pattern of the motion.
Is the input an image or the flow?
It's the flow. So this is the input here, the flow, and then you get this, you want this as an output. And it's actually trained, so the training is done on the ground truth flow and the ground truth segmentation, obviously, and then during testing you take real flow. And so here, this is testing, so the data set is split in a training and a testing set. And here is testing on the ground truth optical flow, and you can see that the results are really very good. So here, for example, even these thin objects are segmented out perfectly. And the one failure case would be here. This is this chair which is moving on a background, and what you can see, it's the same problem what you would have if you estimate the homography. The chair is much bigger than the background, and so in this case the thing fails, and basically the largest motion feature cannot capture the motion of the object. So it's kind of explainable, it does what you expect it to do. And then if you look at what it does in real data, so one thing which we did here for the synthetic data, we tested it also obviously on non-ground truth optical flow, and then the performance drops quite by 20%, so it drops quite significantly. So there's a difference obviously between good flow and bad flow, but it still performs reasonably well. So it's not like a drastic drop. And then the other thing which is maybe interesting is better to train it on ground truth flow than on real flow, because you get a better input. And then here, this is some results on the state-of-the-art Davis dataset, which was published at this CVPR, and you can see that results are actually very good, and it actually outperforms the optimal, the motion segmentation state-of-the-art on this dataset. So just by combining this estimated motion segmentation with some object skew. And then, so this was these two things, and then basically we also looked at using synthetic training data for human pose estimation in 3D. And so basically for most of the 2D data sets, there's no annotation of the 3D pose, right? You have the annotated pose in 2D, but you don't have the 3D pose. What you have is 3D pose for artificial data sets such as this one, which is the CMU mocap, or the H3.6 data sets, which are both indoor data sets, and for those you have the images and the 3D pose, okay? So basically, only for constrained environments you have the 3D pose, and that this kind of approach doesn't generalize well to real images. Okay, and so here the idea is to synthesize locally consistent 2D images with associated 3D pose. I won't go into the details, but I just run briefly over the steps. So what you do is you, for each 2D pose, so you start off with the 2D pose, which is a projection of a 3D pose. You take a 3D pose, which you render from any viewpoint, and then you project that into 2D, okay? And then you want to find assemble a consistent image for this 2D pose. And so here, the idea is you match each of the local joints. So you do it locally. Each of the local joints are matched to the best 2D pose in the image. And then given these different combinations of 2D joints, they're voting. You have some voting and blending scheme. And in the end, this distribution map allows you to blend up new 2D images with associated 3D pose. So they're not completely realistic, but what they are, they're locally realistic. And so the hope here is that the CNN, all it needs to do is to process the first layer correctly, and then from there on it just has the information which it needs. And then we train up a classifier which classifies the actions into 1,000 different poses and uses those as the associated 3D pose. And we use the first results we measure is on human 3.6. And then here are the results. This would be just comparing training on real and synthetic. So you can see that if you train on 17,000, 190,000 real images, obviously the performance, this is 3D pose error in 3 millimeters, which is standard, improves significantly. And then what's interesting, if you use a smaller number, so 17,000 2D images and then 190,000 3D images, the improvement, there's a significant improvement. So due to just injecting these additional 3D poses, and then they're kind of on par, but use much less real 2D data. And then what's also interesting is by combining synthetic and real data, you get a significant improvement in performance. Okay, and then here comparison to the state of the art. So it outperforms the state of the art. And then you also want to know if it works well on 2D images. So here we combined different data sets, MPI and leads for 2D and CMU mocap for 3D. And then if you look at the results, this would be the 3D poses we get for the errors for the estimation in 3D. And you can also measure, obviously the error in 3D we cannot measure because we don't have the annotations, but if you go to 2D we can measure and see that the performance is slightly worse than the best state-of-the-art measures, but they're comparable to, like, say, the methods which were a year before. And obviously our approach is not tailored to 2D pose estimation, it's for 3D pose estimation. And then here, if you look at a few failure cases, so you can actually see that these poses are poses which don't appear in the training data, right? So basically the CMU motion capture data has a lot of walking, running, sitting down actions and so forth, a few sports actions, but these sports were not there. So basically then the poses cannot be recognized correctly. And then we, in parallel, another student of mine implemented an approach where the humans, they're not assembled into images, but we really want to learn sequences. So given the mocap data, we now want to use image rendering techniques and really render the humans, insert them in an environment. Here it's an artificial environment, render the sequences, and then use these sequences to generate, here we generate depth and motion part segmentation output. So here it's really having a human body, its shape. You can simulate lighting conditions, camera conditions, clothing, and mocap data, and use those to assemble a new human associated with 3D pose, body part segmentation, depth, and flow. We also get the surface normals. And then here is the data we get. So you can see it's a superposition of the image. We haven't inserted it yet into some realistic 3D environment. So basically they're hanging somehow in the air. But the humans are realistic, and the sequence of humans we get follow the temporal dynamics of the mocap sequences. And then here. Okay. And then here an example. So then we use those to estimate the body parts and the depth. So here we would have the ground truth and depth and body part segmentation, and here the predictive segmentation and the predictive depth So what you can see here, for example, the hands, the depth is quantized into different intervals for prediction, and you can see here, for example, the hands are not predicted well. They're too fine, right, for this depth estimation procedure. And what's also interesting to see is here, actually, the predicted segmentation is almost better than the ground truth, and this is because the ground truth kind of has some assignment error for the triangle. So if one triangle falls into one body part, it's colored in one color and otherwise in the other color. But overall, you can see for this constrained environment, the results are very good. And so here we only use synthetic data, right? So only use synthetic data to predict this. And you can also show that, so for depth, there's no annotations, and for body part segmentation, we also trained it, evaluated on the Freiburg sitting people data set, where there are people, and there we can show that by combining synthetic and real data, we get a slight boost in performance, but synthetic data by itself already works very well. And then these are results for the MPI post data set. So here again, you can see that for the cases where there's limited number of humans, it works very well. So here, for example, this one guy, you can see we predict the pose correctly, the body parts. And the limitations here are actually when there are several people standing around. So then we kind of start to miss people, and it doesn't work as well. And so that's kind of where you can see that basically the synthetic data, we need to go a step further and put several humans in this together to kind of train up how to process several humans jointly. That's kind of the design issues. So basically, these are the design issues, how to create these synthetic data sets, because they should be as real as possible if you want to really train and use it in realistic environments. Okay, thank you.
All right, don't take off your thing, because let's get the speakers on the stage. Rob, and actually, there's one more here. Yes, here. Yeah, you're on the stage as well. The more the merrier. Yeah, you're.
Why did you say I should keep this?
Because I think they want to.
No, pass this between them.
Oh, okay. All right. So, so we had a bunch of topics that we can riff on ourselves without you guys, but then we could do that also in some pub. So, you know, yeah. So I think maybe we should, you know, have the audience involved here and have you guys ask us kind of forward-looking questions about, what the future holds. Actually, maybe to start things off, we can start with kind of a generic thing. What do the panelists think is going to happen next in the predicting the future kind of regime? Is everything else is deep learning going to subsume all of computer vision? There will be nothing else but deep learning, or will in 2 years it will be something else new? It used to be base nets, and it was SVMs, and it's neural networks. Maybe it's going to be decision trees next. I don't know. What's going to be next? Any prediction? Make one prediction.
No, I think neural nets will be like matrix multiplication. You won't even mention in your paper that you used it. It will just be a tool, just like you don't say a paper, I solved optical flow using matrix multiplication. You will no longer write a paper saying I used neural nets. It'll just be a tool, one of many tools. And yeah, that's sort of the strong prediction. In general, I think, as you said, the vision community is very, very opportunistic about new tools. So I'm sure there will be new exciting tools as well.
Okay, so I think one thing that we'll see a bit more of is combining the deep nets, which are really just purely feed forward at the moment, with some kind of top-down component. So, for example, like some graphical models. If you do have some clear structure to your problem, you want to incorporate, then it's natural to do that with some kind of graphical model. You can stick on top of the neural net and then sort of train the whole thing together. So if you fact, if you historically, some of those early systems that people like Jan and Leon were too trained for their, reading digits on envelopes and stuff like that, and checks, they did actually have this structure of, essentially a kind of structured model on top with, some neural net to get good, good individual digit recognition, and then the structured model will kind of combine it into a zip code or a total check quantity or something like that. So I think we'll see more. We already see people like Raquel Edison and people like that work on these things. I think that's a very promising direction.
Yeah, so I think they'll at least stay around for a while. I mean, I don't know if they're stay around forever, but I mean, as I said during my talk, there are many things now which are possible, which weren't possible, and they give an input to the next level of algorithms. What kind they are? Are they graphical models or some kind of complicated network structures, or something else which is trained end to end? I mean, there's many things you can imagine, and maybe one thing which I think will come over the next decade is robotics. I mean, that's something which Rob mentioned briefly, and I think there's a lot of things which are still very much in its infancies, but the robots start to work, vision starts to work, and if both start to work, we can start putting it together and understand how much we can learn from there and how much we can actually go to the next step, which is interaction with the world, right? Which is, at least for me, that was like my starting point, was somehow that I wanted to have the robot interact with the world, and then once you realize that vision is so bad, then I thought it's better to concentrate on one sub problem, and I mean, I think that's one thing where we can go back to.
I guess I should make my own prediction. So something controversial. So I will controversially predict that, as usual, it's not even a prediction because it's always true. People have been overestimating the algorithms and underestimating the data. So my prediction is that in the next few years we will appreciate more of what's happening in terms of data than in terms of the actual algorithms or architectures. In a way that, for example, yes, we have deep nets have the best score on ImageNet, but nobody has really run any other high capacity algorithm on the full ImageNet just because it's so huge, right? And yeah, not but it's not that high capacity. No, but okay, but random forests are not that high capacity actually.
Okay, so yeah, I mean, I have been told, because but that some of the Microsoft gangs, who had a lot of investment in random forest technology,
Right.
did try to sort of see whether they could get good results on things like ImageNet.
No, but random forest, there is a number of clear problems with random forest. One of the important ones is first of all, when you think about random forest, you think it's a huge forest, it's like thousands of things. No, it's like 6, right? So
Well,
it's not very high capacity.
Well, no, but you have the ability to just increase the depth of each tree, right?
But
So-
then
so
every
it's-
time you increase the depth, you have less. You half the amount of data you're training.
Sure, I mean,
So
but,
I'm
it's-
waiting for somebody
but-
to run near Sniper, frankly. So, but like you yourself said, you say, wow, if you do random network, sometimes it does pretty well, and we have found this too. And in fact, Gaddis had a beautiful paper that says, what style transfer. If you take a random network instead of the pre-trained network and do the style transfer, it works pretty much just as well. So I'm not saying that it's all ends up being equivalent to nearest neighbor, but I think neural networks will turn out to be closer to nearest neighbor than people conventionally now think. So that's my, we can bet a gelato on this.
But these convolutional neural networks, they have actually 2 layers, right? That's kind of fundamentally different. The convolutional layer and this stacked layer of fully connected layers.
Okay, but Rob just said that fully connected stuff doesn't really.
I mean, I think, but you don't necessarily need the fully connecteds aren't sort of crucial.
Yeah, but for example, what people have shown, they have shown some standard features, and they put it like several deeply connected layers on top of it. That worked pretty well as well. I mean, that's something which works very well, because then you have this high capacity, right? So I think for me, the deep layers is like really this convolutional architecture, which kind of cleverly assembles
No,
features.
okay. Let me modify. My prediction would be that things are going to turn out to be simpler than we think now. There's going to be something that will say, oh.
It's certainly true that there's very little deep understanding of what these models are really doing. So it's certainly true that once we have if people might uncover things, yes, that are a great deal simpler that work. I mean that's certainly a possibility.
All right, now that we've warmed ourselves up, okay, go for it. Good.
Oh, okay. Okay, so basically, are we just fooling ourselves, thinking that neural networks do something better just because we're measuring the wrong thing?
Okay, so I would say that some of these benchmarks are sort of useful enough in the sense that the networks that do well on them do well on tasks that are genuinely used in practice. So if you can do well on ImageNet, then you do well on, say, running on side inside Facebook or something like that. The data is different, but it's the metric or the is useful enough. So I think it's a bit of an open-ended question. What problem are you trying to solve? But it's certainly for the problem of doing image classification. If you care about that, then I think the deep nets seem to be very effective.
For object detection, they have shown real progress, right? If you look at the videos we saw yesterday at Mobile Eye, the cars there are all localized and tracked and blah, blah, blah. So I think this is how things which are success. Maybe to reformulate what you said or slightly differently, there are problems which we don't consider at all, right? So we have focalized on some subset of problems, and that's kind of what we're operating on, and now we're very happy. And now it's maybe time to think of what are the other problems we haven't even thought about, or we're just not considering because we consider them too difficult or something, right? Because image classification A is maybe not so interesting, and object detection might be also not the end of the story, right?
I think in spirit I agree with Daphne in the sense that, as always, you have to distinguish between the hype and the truth. And when people say published papers that on image classification now neural networks do better than humans, and what they bring as a data point is they ask humans to classify do the exact same task in ImageNet as the networks are, and people are not as good as the network. But then Alyosha shows us this thing that doesn't look like an ostrich at all, whereas the network says this is an ostrich. And I think there are many examples of this that there's a difference between the interpretation we give to the performance in the data set versus the general purpose problem that we're trying to solve. That said, it's a broader class in the class of all image classification. So maybe internet imagery is one way to define the success. This again goes back to Alyosha's talk today. So I think internet images are a very small subset. Images that people post to Flickr or whatever, which is what Facebook is interested in, after all, is a small subset of the world of possible images. But from a business standpoint, just doing very well on these images is very meaningful. So for example, faces, this is a point that Sandy Pentland made many years ago, that some huge fraction of the images that people look at and take are images of faces. So if you do well on faces, that will have tremendous benefits commercially, but that doesn't mean you've solved all of recognition.
All right. Students, yes. That's a good idea. That's excellent.
So in the era of neural networks, data is king and computational power is like queen. What would you suggest a young researcher in a medium-sized university that cannot afford to compete with Google or Facebook in the extent of data and computational power.
Internships?
What Rob's going to answer.
Rob, yeah.
So I mean, I think if you think about these unsupervised learning problems, then the whole problem of having to get lots of label data goes away. So that the king is sort of out of the question. But it's still true that it's hard with it's hard to do things when you have to wait a week to sort of see how your experiment turned out. So that part is difficult. I mean, I would hope that NVIDIA loses its sort of monopoly basically on the GPU thing. I mean, if Intel gets its act together, then maybe the prices will come way down, and then we can all have a lot more compute. So I do. The other thing to say is I think the cloud computing providers like Amazon and Microsoft, Azure, and things like that are getting their act together with high-end GPUs actually. So I think very shortly it'll be much easier to sort of. But of course, it still won't be. It still will cost money if you're running a lot of stuff. But perhaps that will help a little bit.
Yeah, so actually, we had this discussion over lunch, and so my take on this is like, if you have 1 or 2 GPUs, I mean, okay, you're not as good off, but in many cases you can actually do what you want to do, and maybe think a bit more, and then before running the experiments, if you think more, then it actually works better. It's similar what I've observed in what this huge cluster. So somehow people didn't optimize their programs anymore, and in the end of the day, we didn't get more results out. I mean, there are things, okay, I'm open the brackets, there are things like checkers which we cannot do without a cluster computer because it's too big. But other than that, I found that having more computer power in many cases are actually just people are less careless, or they just, if they know they have 20 GPUs free today, they just run stuff without even thinking, and a week later they get like all the results and 90% of them are incorrect. So I think this is like encouraging. If you're in a small lab, okay, you need a minimum, okay, you have to define what's your minimum and then try to think before running the stuff, and then I think you're well enough off, and there are many pre-trained networks around which you can actually use, and gives you a good starting point to understand actually what's good. So maybe the things which you cannot do, you cannot create this large scale billion data sets. This is something you cannot do in your lab, okay, fine. And then the other thing, you cannot invent a new network architecture as ResNet. To invent ResNet, you have to be at Microsoft to have 100 GPUs and run everything in all the possible experiments. But other than that, I think you're able to do research.
And I think putting things in perspective, I was in some workshop, I was complaining about, we could only do this because, it took 1 month to train the system, and so we had to stop. And a great neuroscientist, Jack Gallen, he came up to say, this is bullshit, this is ridiculous. I have PhD students in my biology lab that do one experiment for 4 years. 4 years, and you're not willing to run some GPU for a month, right? And I think this is a very good point, that we are still so much better off than the other sciences, the experimental sciences, like biologists. We should really count our blessings and not complain, because really it could be much worse. And 1 month to do an experiment is not so bad. Well, work on something that is so fundamental that other people wouldn't think about it.
So we should study neural networks as biologists study bees or other animals. So that's a new type of animal-born neural network that we should study.
So since my PhD is in brain and cognitive science, I can take a stab at this. Studying but bees is very difficult, and probably a different skill than what most computer vision people have. So maybe that's the best we can do, but I don't think that's the most likely to succeed path to moving forward in research. I think if you just look at organisms that have, say, 200 neurons, and all the connectivity is known, neuroscientists still don't understand them, and they don't understand how they behave. So the chance of understanding something like GoogleNet or one of the Facebook things, using these tools, I think it's impossible. I think what we should do is we should actually, design systems that are not just black box neural nets, and then we'll understand them much better. And I agree with Alyosha that those in the end will also work better. So that would be my suggestion.
So if you think about what we need for a general purpose robot, you expect this robot to accomplish like a huge variety of tasks. But right now it seems like we're training a separate neural net for every single task. And do you foresee there's going to be some sort of unification of these at some point?
Yes. Yes, for sure. So I mean, I think you have a common trunk, and then you have different heads essentially for different tasks. And I mean, this, that's how things work in industry and stuff too. Where you can't afford to run a separate network for everything you care about on the image. You have to have a single core piece and then different heads.
There's a nice paper by Amnon Shashua and Shai Shalev Schwartz, specifically about autonomous driving, arguing that sort of end-to-end training of autonomous driving is not the way to go, because of the same reason that you said, that basically a driver has to solve many, many tasks. And actually for theoretical reasons that they put forth in the paper, trying to do all of these together is much less likely to succeed than training separate modules separately and then combining the results in using sort of logic and probability. And so I think if you're interested in that, I would recommend reading the paper. And no, it's a separate paper. Again, the argument is that if you need to solve 100 different things and you sort of train everything, automatically there's something that's exponential to 100. The number of training examples you need in some sense grows exponentially, whereas if you break it up into smaller parts and train everyone separately and then combine later, then it's linear and not exponential. So I recommend this paper.
But also Judea's Pearl's book, right? The compositionality.
Yes, this is
basically the fundamental of
right.
learning.
And this is the exact same point that Judea Pearl made for unsupervised learning. Trying to learn everything simultaneously requires exponentially large amounts of data, where splitting it up and then combining is really the way to go.
Sorry, just on that note, I think the one thing we don't talk about too much in vision, but you see a bit more in some of these other fields of deep learning, is where you have a curriculum. So you have software with simple examples. So if you have a multitude of tasks, you maybe have simple tasks to start with, and then you have sort of tasks that involve compositions of those and so on and so forth. So that way you sort of you do get a chance to kind of you're not trying to do everything all at once from the get-go. And it proves very decisive in terms of getting models to work.
Well, I think maybe. Okay, I think maybe this is the first time that we come back to the original AI problem. See, AI when we view the whole AI problem, then computer vision or visual processing is part of it. And so a long time ago, actually very early AI, representation was the central issue. So the interesting question, and then of course, when we started vision, there was no good capability, so we chose probably like a classification, object class, or location. Those are the vocabularies that the vision should answer, and we didn't answer that well. Now, for the first time, it began to do pretty well. So the next question is, are they the appropriate language or representation with which other components of intelligence communicate? See, for example, now at least human explain. So I have one example of Rob say which next video, and in a short range, yes, it may be a signal problem. But when we see, say, basketball, is somebody get the very rough play, and then a few minutes later, we anticipate some kind of fighting might occur, and then whether it occurs or not, and so forth, depends on whether the two players had some issue in the last, or if they were friendly, or and so forth. Then depending on that, the difference. And then, of course, when we explain human, we use all these natural language because that's the only way we communicate with others. So the interesting question is, what is the right one? And indeed, even within visual understanding, I guess the communication is not at the level of image or coordinate system, but some sort of a decision, and then goes to at least what used to be called very logical referencing. Like my usual example is that when somebody recognizes a scene, say Japanese scene, and then they think that, oh, this is the culture is this and that, and then, oh, in this country people drive in left side, and therefore you make a decision which visually no way to get a decision, but somehow that sort of going this long path will make it possible. So maybe we might be just starting the air, which we need this type of capability, and then you may, or younger people may have made it for the first time possible.
Well, so just to take the one example you gave there of the basketball players elbowing each other and then some time later on seeing a fight. I think actually this should be, that kind of signal should be predictable right now. So Cordelia's got was showing sort of action recognition. So if you had features that were good for action recognition, I mean, if you then had a sort of predictive model in that space, you could perhaps predict, you've seen an elbow action at some point in the future you might expect to see. So that's that sort of.
Yeah, but still though, as I said, whether those two people had a previous issue or not, those are not a visual. Well, of course, it goes all the way back to some visual phenomena, maybe, but maybe that's 2 years ago. Well, sorry to spend a lot of time. One other thing, though, is the vision is not just what we people do. Because computer vision is, I usually call it measurement device. And it already as a measurement device, like, I think Shri said that it's quite a bit surpassed human in many regards. And I think that's a different aspect of vision, and these days everything is recognition, classification, and so forth, and that might be swinging the central gravity too much to one end, whereas real physical, real impact may be, I shouldn't say real, but at least quite a bit of impact maybe on the other side of computer vision, which is the system which measure things. We shouldn't forget that. Indeed, that's cheaper to do, though. Somebody said, you may not need that much money to do that.
Okay, I want to get more questions and comments from the students.
So my question is that I'm getting to think that neural networks can solve any problem, and if you add like more data, more parameters, more layers, you can solve anything. You can bring up world peace and cure cancer. But in your opinion, what are the things that we cannot solve with neural networks, and especially with these architectures? Are there any, I may rephrase it as adding more data and still not understanding what's happening under the hood, sorry. What's the barrier? How far can we go with these neural network architectures?
So I have an example that's not in computer vision, which is a very clear example of something you can't solve with more data. So that would be if you try to teach computers to do simple things like read in a sequence of digits and then spit it back to you in reverse. Okay? And so you can generate sort of essentially unlimited amounts of training data for this, right? And what you see is that the networks will work really well on your training data, and you'll be convinced, oh, it's understood the algorithm, the underlying algorithm that's trying to in question. And or you can try things like addition or simple things like that. But what you'll find is if you take a test time, a sequence which is now a lot longer than the ones you expose it to at training time, it will fail. Okay, and so you can have because it's completely synthetic, you can have as much trained data as you want, and you can make the models as big as you want. In fact, making the models bigger exacerbates this problem. And so if you ask me, there's a clear sort of deficiency there in the models we have. They're not able to sort of abstract out the underlying algorithm, even though it's an incredibly simple algorithm. So that's one clear failure.
I think the problems Takio just mentioned are like all, I mean, okay, Alyosha will say more data, but I think at some point there's not all data. You don't want to model all the situations, right? So if somebody gets into a fight, maybe you want to know that there's a fight, and then maybe they go back or whatever, elbow, and then fight. But maybe that's something where we have to have something else than just some simple training data or some simple deep learning. Maybe you want to go at some point back to some, I don't want to say rule-based system, but to have something which is a higher component of logic, which we train either with whatever LSTMs or just some rules. So I think that's the next challenge, really, to know how to model these things, because right now we're all still stuck and struggling with the basics. I think it's maybe time now to think of the next layer and to see actually where were people 30 years ago or 20 years ago when they wanted to solve AI. This is typically an AI problem, or this block thing was also a typical AI problem, which people then just couldn't recognize their cubes, and then they just gave up on it, right? And so basically now we can recognize the cubes, and then maybe we can actually start thinking of how to go back to all these much more evolved problems.
I think it's important to keep in mind in answering and thinking about your question is that people sometimes have something with neural networks that I call a suspension of disbelief, meaning they really believe that you can learn anything, and they forget what they learned in probably the first lecture, Introduction to Machine Learning, that there's no algorithm that can learn anything. There's no such thing, and neural networks are still an algorithm. So any learning problem requires what's known as inductive bias. No matter how many examples you give me, if there's no restriction on the function that I'm trying to learn, I can't predict the next data point. So, and this is a very fundamental thing that people seem to forget when they talk about neural networks, partly because of the hype and partly because of this. So I think really it's important to keep in mind that it's a learning algorithm, and so it's still bound by the laws of computational learning. Nothing can do a perfect extrapolation, right? That's the point. There's no such thing. It simply does not exist unless you somehow restrict the problem set. There's no such thing as a perfect extrapolator, and that's important to remember. And part of, I think, the challenge in neural network theory is trying to understand what is the inductive bias that the convolution pooling architecture imposes on the problem. So it's not the same inductive bias as we had when we're using regularization. Use L1 versus L2, and you sort of understand those regularizers. But the architecture that we use for neural networks, that's a kind of a regularizer that we don't really understand. And the other data point that I think Rob told me this, and that others have known, is the amount of time it took Alex Krzyzewski and Ilya Sutskever to figure out the right architecture for ImageNet was over a year. Yeah? 6 months of just trying a lot of architectures until they settled on the one that would have the right inductive bias and would give you the right answer. So please remember this. There's no such thing as learning without some kind of inductive bias. And there's no such thing as an algorithm that can learn anything.
Well, okay, I want to be a little contrarian here. I think there are in some scenarios, some limited domains that we can actually just solve the problem with neural networks, just like we could have solved it with nearest neighbors, except it would be too slow, right? And my suspicion that a lot of kind of real world industrial, especially problems, are that kind of problems. I wonder if, driving, especially on the freeway, is a type of problem where you could just get all the data, right? So because then you don't even need to interpolate, you just look up. It's really just nearest neighbor, and neural networks just make it super, super fast. They basically can give you nearest neighbors really, really fast. So in that sense, I think there is a group of problems which are very much solvable now. And I think that's 90% of the excitement in the industry is basically in that scenario where you basically can populate the space. I mean, MNIST, for example. MNIST is basically, it populates the entire space of digits, 10 times over, right? There is no need to do any interpolation. It just, nearest neighbor actually does pretty well there. But because we humans are around, or any kind of animals are around, because of our ability to evolve to changing conditions. That's, I think, what makes it kind of interesting for us, right? That our learning machinery is able to function in a future unknown environment, right? So our test data is never the same as our training data. We are never in this beautiful machine learning paradigm of you divide your data in two, one you use for training, one you use for testing. And that's what makes it exciting. And that's what makes us suboptimal in some problems, but also very optimal in many others, because we are built for changing environments, and our algorithms are not yet.
Cordelia, she showed that in all these contexts that we talked, in the pose estimation, that once you gave them poses that were not in your training data, although you had a lot of data because it was synthetic one, you couldn't predict that. So do you think so this is an example for compositionality and nearest neighbor, but do you think maybe it's an issue of regularization? Like if you have a better regularization, you might embed everything to a better, smoother manifold, and then you could predict compositions that you never saw before?
So if it's completely different, I think no. I mean, okay, you can always try to regularize and maybe by chance you get it out, but I mean, it's clear that if, I mean, say you only see upright pedestrians and then all of a sudden they all lie, I mean, it's just, you can regularize as long as you want, you're not going to get them, right? So, well, if you turn them during training, I think that's also one thing where knowledge comes in, right? Because that's kind of, when you generate this data, some sort of knowledge comes in because you have to see what do you want, right? If you start creating the data or curating the data, I mean, that's something. Nearest neighbor, okay, Alyosha says we take everything, but somehow you cannot store everything, and also there's some bias, right? If you have 100 people walking and only one person jumping, somehow your search might get whatever, overcrowded, overweighted, and I think that's something which is actually important when you curate your data, is like how to present it, right? Because that's something, especially for neural networks, but maybe also for other algorithms. So if you have 100 sequences of walking and one for crouching, then you'll just get this bias towards walking.
Professor.
I actually disagree with you. What?
Kind of.
Hmm?
Somewhat more. Yeah.
I disagree with you, Alyosha, when you say that.
We're bringing the dirty laundry out of the kitchen.
Out. You say that neural networks, the way they are now, are enough to solve driving in the highway, and I don't think that's true, because you can never get training data, real-life training data, for all the emergency situations that might come up, which are important. And
I think on the highway you can. There aren't that many.
You're going to volunteer?
So many accidents per day. Just everybody has a little camera.
I think this is where you need synthetic data.
That's actually my question to Rob, actually, because I think the main criticism of using feed-forward, discriminative type neural networks for prediction is that you can only predict the very, very near future, because it's very, very regular in a way. The world is a regular place. But if you try to predict something further away, this breaks down, because you might have to do something more modular or something like that. So my question is, why did you choose to do this brute force end-to-end architecture for prediction instead of looking for something more?
Well, okay, so I think we just wanted to see whether it would work at all. It wasn't, I mean, these days, of course, no one's that surprised when the neural nets do end up working reasonably, but I mean, it is having to internalize things like, Newtonian mechanics and stuff like that, and we didn't want to hand code it at all, which is what the other approaches were doing. So it was able to do that. I mean, I'm for sure predicting things a long time in the future is a very hard task. It's not clear to me that the neural networks will be any worse at it than perhaps other approaches necessarily. I mean, it's true that there's no direct experimental evidence in the stuff we did to sort of probe that. But I mean, there's always going to be sort of an uncertainty will kind of explode as you go forward in time. But I don't see that the nets necessarily will be that necessarily worse than other ways of doing it.
So our community has been grinding CNNs to death in the last 2 or 3 years. But I haven't seen that many works in reinforcement learning. And there's something very appealing about reinforcement learning, which seems to be much more catered towards unsupervised and so on. Can you say something about where you think we can go in vision with reinforcement learning or where its limitations are?
Well, okay, so I think if you have static data sets that are sort of curated from the world, that you get from the world, then it's not quite clear why you need reinforcement learning. I mean, but on the other hand, if you have a robot which is going to take a whole bunch of actions, that
So there is actually a lot of reinforcement learning. Like a third of NIPS was reinforcement learning.
Yeah.
It's just the next wave which is coming. I mean, I would say reinforcement is the next wave which is coming. I mean, if you look at NIPS, it was like vision and robotics and vision.
But it makes sense when you have an agent that can interact with the world, I think.
Yeah, reinforcement for static images is not.
Well, it's not quite clear how it worked there. I mean, you have to get some sort of outcome that requires a sequence of sort of long sequence of actions.
But you could imagine basically an online algorithm. You can imagine a reinforcement learning in an online algorithm that keeps getting new images, even if it's not active, right?
Sure. I mean.
Anyway, I think to answer Mikhail's questions, it's something which is coming. I mean, it's the next. I think NIPS was full of guns and reinforcement learning. I mean, that was like the take-home message in a nutshell. So.
But I don't want to burst your bubble, Michal, but reinforcement learning is also a special case of a learning algorithm, so it will not work for any arbitrary problem. Yes, so I think in reinforcement learning as well, to really things that will generalize to arbitrary environments, there's some model-based in there and inductive bias built in that makes it work. I mean, so I don't think you're not going to get away from the need to have some inductive bias outside the training set, beyond the training set.
Don't forget that deep learning is a subset of what the computer can do, because deep learning is a class of computational mechanism which is neatly carved out from what computer can do, so that its behavior can be under a good leash by designer. Now, of course, somebody may be able to prove that the subset of the function that can be computed by deep learning is equal to the set of functions that computer can compute. That's interesting. Is that proved?
Yeah, actually, one of the interesting thing about this is that even shallow neural networks, that's true, are universal approximators. So there's sort of a debate about why people, but even for shallow, just a single hidden layer unit is what's known as universal approximator, can approximate any function. Yeah, there's a. Yeah, I think there's a difference between the fact that a function class can represent any function class. That's one thing, but the question of how many examples you need and how well you'll generalize is sort of a separate issue. And
if you have a very wide if you're prepared to have an exponentially wide single layer network, and that in theory can represent any function. But what you see, of course, with these deep nets is that they're actually very skinny and tall. So it's just more efficient to sort of have the depth rather than. But of course, it's it's clearly, as Yo is saying, some inductive bias. I mean, that happens perhaps to work well for images at least.
All right, one last question from a student, and then cookies await.
So, when you spoke about how data is king, a lot of researchers tackle the problem with the synthetic engines that can render, a bunch of different variations of scenarios and will allow you to extrapolate to a wide variety of things that maybe like real data you wouldn't be able to do. So the question is, how important is the photorealism in the rendering? Like, is it super important that things look real like they do in the real world, or sort of is it enough to take a second step of like fine-tuning on real data?
I think so far, I mean, I don't know the final answer, but so far it has shown that if you approximate it real and you fine-tune with real data, it's sufficient. But obviously, the better the data, the more realistic the data, the better results. And for me, what is like the take-home message here, it seems that neural networks are much less sensitive to this synthetic and these errors in the data. I don't know exactly why. I guess because it's these levels of abstraction. So basically, once you have fine-tuned the first layer to real data, the other layers, they kind of stay the same, right? Once you have your filters out, then basically the remaining layers are the same. That's kind of why I think it works, right? So basically what you need is to have the first layers tuned separately, and then the other ones, they can kind of remain. And compared to, I mean, we tried training on synthetics a few years back, and it was catastrophic, right? All the SIFT and all the hogs there were completely different, and so we had like a very hard time engineering the last layers to make it work. While now it seems to be just working very well. So I think so.
And there are also some pretty interesting works recently on sort of domain transfer, trying to sort of train networks to ignore the differences between two distributions and stuff like that. So yeah, so that they will work on real data well.
All right. Well, thank you very much.